Thank you. So Ian, of course, this for a lot of us, this conference is dear to our heart. This Center Round conference will be fifth of the series, right? The fifth one. So Ian is certainly the mastermind behind this. He was planning to do the commercial during his 2 minutes introduction, but he realized that he didn't have enough time. So he said, since I don't have too much to say within an hour, I have an hour time, so I'll do this. Yeah. So Jack and I, we are in the scientific committee, and Jack will be one of the keynote speakers. And if you look at the topics, it's actually not just a traditional area. So the new topics, AI and quantum computing, and also low precision computation, very much related to this workshop. And if we're lucky, we will get Rick Stevens from Argonne National Lab. He's currently the overall lead of the DOE Genesis mission. It's the AI initiative. So it's going to be an exciting meeting, okay? Anything else you want to spend time on this? So Ian is here, we're here to answer questions. That's a good point. All right. So it's actually very difficult talk for me to prepare since Aaron asked me to talk about software aspect, and it's a very broad, open-ended software thing. But it's very good. I'm the last one, almost the last day. So I got a lot of inspiration from the discussion over the last 3.5 days. So my focus will be benefits. We all, agree maybe. And then maybe more on the obstacles. So what can we do to overcome that? So over the years, I have a lot of collaborators, particularly last 8, 9 years. So we worked very intensely on the Exascale computing project and fast math projects. For this talk, I got quite a bit input, a lot of input from various colleagues like Hardwick. Give me some very nice slides that you will see soon. So the plan is talk about experience success story we want and obstacles, and also to mention some paths forward, particularly to help modeling and simulation codes in the area of very much low precision. So we'll review a little bit the what happened in the ECP project. This finished a couple of years ago, so it was a 7 years project. And as if you listened to Hardwick when he was doing his self-introduction, he said, "This is my best or one of my best projects." So it's really good. So the thing is, at that time, we had a lot of resources and all the big code. So these 25 applications, these are not a library. So these applications, they were moved to GPU. If without these resources, it's not possible, even for our library. So then you can look at their programming models they use, a variety of them. I think it's probably not very surprising. So a lot of people doing this GPU-specific kernels, they rewrite everything, so it's quite labor-intensive. And then quite a few applications, they use this loop pragma. So I was talking to Rio. He said in Japan, maybe a lot of people, they are using this OpenMP or OpenACC instead of directly programming CUDA. So that's still a very viable approach. And then if people, a lot of these codes, they were in Fortran. Some of them, they restarted from scratch, written in C++. Then you have a better abstraction, better, say, operator overloading template, etc. So one of these two things actually are COCOs, for example. These are were developed from scratch from National Security Lab. that side. COCOS, I heard from this discussion here, is actually picked up very broadly, quite broadly in Europe. So which means you write in COCOS syntax, it's going to be able to run on Intel GPU, NVIDIA and AMD GPU. So that's also a very good programming model. So Hardwick actually was leading this initiative. It started in 2020 in ECP. And the reason it started is after 3 years into ECP, then we did the gap analysis to see what's missing in our original plan, in DOE original plan. So it turns out there the main missing piece is we were not taking advantage of the hardware speed, the GPU speed, by doing lower than 32-bit, for example. So this is one of the gap. But certainly this gap was very difficult to fill by the application people. So we decided to start from the math libraries. And then one of the significant products out of this is the survey article. Hardwick organized, there are 21 authors, and we certainly, Nick and Stan, they were, sorely missed now. So the general picture here is that people usually just think at a very high level. First order approximation is every precision you have, then you should be able to solve 2 times larger the problem. And on the CPU, you want to expect to have 2x speed up, but the speed up is even more on GPU. So that's the general picture. So I'll give you several examples about this mixed precision result. The first one is the FFT. It's Hefty was led by Stan. He did he led this part of the work. And you can see for FFT, using the mixed precision, you can get up to about 4x speed up. So the experiment, the code here set up is, so there's several curves. One is CR4, the most performing one, is the FP16 mixed with FP32. So floating point operation is FP32, but the memory storage and the MPI communication is FP16. So you get 4x faster with the increasing number of GPU. So this is a little bit like a memory accessor, but it's not doing too fancy, like not the adaptive precision, certainly. So another example is sparse direct solver SuperLU, and this was done in my team. And this example show you doing the single precision sparse LU factorization, then iterate refinement in double precision. So this is well understood mathematically. And here we're just showing, even in the sparse situation, you do get a benefit. So the picture here is the speed. We're comparing pure double and the single, then the mixed with single plus IR double. And this is increasing number of GPU. So by the time you use 48 GPU, it's already cross nodes. So that means you have to do MPI communication. So even adding this communication time, you can see that the mix is still like 50% better than the double precision, pure double precision, and faster. And the left side showed the convergence rate of 2 metrics. One is the forward error bound, one is the backward error. So with this single with IR, and you can, backward error, you can always get down to what the machine epsilon. But forward error will be related to a condition number. But if you just do working precision iterate refinement, this blue one, you won't be able to get convergence. So that's, again, it's well understood, but just want to show you in the sparse case. So memory accessor, since last couple of days, we saw the Tails talk and a lot of discussion. We don't need to say too much about this, but I consider it's one of the significant innovations in Ginkgo library. This started, the paper was 2022, but it started a few years earlier, right, Hardwick. So it started in Ginkgo, and then Mump's team picked this up. I mean, not picked up, I think you did maybe independently. So then they used this in the direct solver, also used this in the block low rank solver. They have very recent, they had a comprehensive paper about this, and you heard Teo's talk. So this precision custom FP times will be more flexible than just 16, 32, 64, etc. So you can do some combination of exponent mantis, then it's called reduced precision. So I will show you some of the results of different algorithms from Ginkgo about this memory accessor advantage. So the first slide showed here is the roofline, what you get roofline of different precision. It's on the Grace Hopper, and also compared to the CPU. So the host is this machine, the CPU, and then the label without host is on the GPU. So you can see that at the first level between a host and the GPU, the roofline is already maybe order of magnitude difference. So you have quite a bit performance gain from GPU. And then if you look at the GPU curves there, we can take a look at the accessor. So it's a 64-bit operation, but 32-bit storage. This is one kind of accessor. Another accessor is compared with FP64, for example. So these two compare. Then you can see the gap is by these two curves. So even the memory bandwidth, certainly this is known, but this slide just quantified the benefit. So another example from Ginkgo is the mixed precision AMG on GPU. And very often AMG is not used as a single solver, it's used as a preconditioner. So you solve the transformed linear system. This P is computed by multigrid. The P inversion is computed by multigrid. So in this particular setup, they are doing the higher precision in the fine level, let's say the finest level, and then lower precision at the coarser level, either doing the smoother or something, then this correction is propagated back, error correction is propagated back to the finer level. And the performance here is showing they actually integrated this into this MFAM code, is the finite element code. And the two pictures shows one is in the beam application, one is in the L shape, the geometry, another application. And then the three bars, one is the NVIDIA AMG X in double precision. The blue bar is the AMG double precision from their code, and then the multi-precision AMG, their new one. So you can see that multi-precision always has an advantage, and the accuracy they get, not in this chart, but they get a good accuracy. So it's also successful for multi-grid. And what about a Krylov solver? So this is one kind of algorithm they do. It's called a compressed basis, GMRES, meaning that they use lower precision only to store the for the Krylov basis vectors. But every computation is arithmetic is double precision. So the implication here is a little bit gray, the text. There are several implications. One is the search direction may not be double precision orthogonal. And then the Heisenberg system maps solution to a perturbed Krylov subspace. So then you may need more iteration, etc., and maybe not convergent at all. So the statement here says, as long as the loss of orthogonality is moderate, then you should be okay. So this picture shows that, again, the notation here, the first one is arithmetic, the second one is the memory precision. So for example, for this red line, you will be in trouble. So if you want to get down to 10 to the minus 10, maybe you won't be able to get there. So this is a more comprehensive result from this compressed basis GMRS. On the horizontal axis, you can see about 20, 30 sparse matrices from sweet sparse. And the vertical axis, there are two pictures. The top picture is about a normalized residual norm of when using this different algorithm. And the second picture is about speed up. So for different algorithms, there are a lot of different, it looks like a bit messy, but for all matrices, so it's very consistent that this one, I think GMRS FP64 into 32 or FP32. So either using integer or floating point 32-bit storage is you get a good enough at the bottom there in terms of residual. And the speed up uniformly, you can get roughly like 40% or 50% speed up. So for this algorithm, the message is that 16-bit is not enough. You have to store 32-bit. All right. So now I'm shifting to the now. Are there any questions? So that's a part of history, yeah.
For the GMRS stuff, are they using flexi GMRS or are they using some kind of iterative refinement?
It's just a restart, Hardwick, is that true? Yeah, so the restart 100, yeah. All right. Okay, so ECP ended, not good news. But so there's still program, DOE still has a program going forward to support applied math research, development, software, etc. It's just, I think the biggest problem right now is the funding level is not as aggregate, as big as the ECP era. So we have to piece together a lot of different funding sources, and then it's difficult to get how do you say, the critical mass to do this stuff. But the fast math is this fast math, the sixth cycle. So SciDac, the DOE started this program about 2001. So now it's in the sixth cycle. Every 4 or 5 years is one cycle. So we'll continue, and as you see, there are a lot of people involved. So every person, it's not ideal. Every person is actually get a small fraction of the time to do this. But we have focus areas. It covers almost the entire, I mean not entire, but a big chunk of the applied math in support of simulation. So this algebraic solvers, including eigensolver, linear system, and discretization to do the meshing, and decision support is the optimization, a lot of optimization algorithm and uncertainty quantification. And one of the things very much related to this workshop is the cross-cutting activities. So in the cross-cutting activity, we were talking about hardware-aware algorithms. So this will be very much related to the software hardware co-design, this breakout group, and also very much related to John's area. So we're hoping to have more conversation. And then the energy-aware algorithm, then the mixed precision arithmetic, trying to get this into all these solvers, discretization, etc. And then a big chunk of more than 20%, I think, of the funding is actually dedicated to software stewardship. Make sure all these have a good support, have a bug fix with the user interface if user have questions, etc. So that's also very important. So because of this, the workshop that I'm asked to come, And then we started this about a year ago, this FastMath 6 with this mixed precision. It's a very, I would say it's not so easy to agree upon a lot of things, very divergent views from different teams. So then about a month ago, we started this questionnaire to FastMath teams. You don't need to read detail right now, but I'll show you what are the answers. So we have about 15 libraries altogether in FastMath, but really doing the floating point operations are about these 9 different libraries. These, if you recognize the names of this, most of them, they are, I would say most of them, they are really in production level. So you can install either from CMake or use a spec to do installation on any MPI machine. The only one which is started is just started a year ago. It's this FastEig. Is trying to do the eigensolver, compute eigenpairs, perform spectral analysis for targeting for sparse systems. So this one is not as production as the others. And the order here I'm listing is from simplest, maybe more like a kernel-based or single-purpose solver, to more framework, like PET-C, as you know, it's a lot of function. It's really for people, the framework for people to build a PDE solver. And then this finite element package, which Hardwick have integrated Ginkgo in there. And then AMRX, that's John has showed some result about this adaptive mesh refinement. And it's very broad. And also, even though just the 9 packages, I would think it represents a lot of application needs, maybe most of the application needs. Also, I'll show you the answer. People answered the questionnaire. It's very conservative. It seems like too conservative. But one of the reasons is these packages, during the ECP time, we spent a lot of time to make them interoperable. So that means in one application, you can call simultaneously 3 packages. You can install and call them 3 or 4 together. So this makes doing mixed precision support is also very difficult. You have to make sure that everyone you follow the same practice or agreement on something. Any questions about these features of these packages? Okay, so let's come back to the questionnaire. So the first 3 questions are relatively simple. First question is just, what are the most common precisions the library is used by the user? Not the common precision you are doing, but the user. And most of the time is double, no surprise, followed by single. And then what precision do you currently support? So that's a little surprise to me. I'll show you this PET-C. PET-C, they actually support 16 up to 128. And the hyper is multi-grid. It has this, then they are interested, they are supporting, so that's why they have this higher precision. So I missed, yeah. And Sundial is a time integrator. They have traditional just 2 types, but they do support extended. So that's a little surprise to me. And then the next question is, what reduced the precision you are interested to support? Most people, they replied that they want FP16, but not lower. so they actually, people are interested in FP16. So I'll spend a couple of minutes review this PET-C multi-precision support. So PET-C is, it's a very big package, right? A lot of features. I'm very impressed, I would say, that they are willing to support 16 and 128. So at the configure time, when you say PET-C, you say configure with this option precision, then you can specify this. And internally, they will check if the compiler supports this. If the compiler supports, then they will do it. And then for external packages, they can build with respect, user ask for single or double, and suppose they ask a single precision, but then they say we need a direct solver underneath. So then they can support external packages, say run PET-C in double, MUMPS or SuperLU in single precision. And in addition to this compile time static checking, the linking, and they have some set of additional runtime checking. So for example, if the on the real machine, if they discover that FP16 is not supported, then they will you will get runtime error like this. Or it's you can use FP16 for a real number but not a complex number. I don't understand why is that. So then you can say this 128 mostly supported by GCC, the GCC 4.6 or G Fortran, okay. And for GPU, currently they are pretty conservative. They only allow single and double, not a lower precision, even though the speed benefit of lower precision, it really comes from GPU. So those three questions were relatively easy, are about the precision. Now we get to harder question is mixed precision. So what this question is, what mixed precision algorithm you are currently supporting or plan to support in the future? And currently mixed precision support is very limited. That's not a surprise. And several people expressed the interest in mixing the double single or double quad. But they are, the next bullet is none of the respond expressed the interest in mixing with the FP16. So I think I haven't asked them what are the reason, but I think even mathematically people are concerned about mixing, say, double or single with a 16. What's the outcome? And then there are some examples, so like a COCO's kernel. COCO's kernel is mathematical, various mathematical algorithms built on top of COCO's language ecosystem. And then because a lot of their operations are relatively single purpose, so they can support a fairly good amount of lower precision. So they can support Osaka scheme using integer emulation for GEM and for iterate refinement in GMRES. And in multi-grid, precision, they can vary with the hierarchy at the different level of hierarchy. That's put in Tridino's package. So which means that you're, instead of like in the Ginkgo's, AMG has maybe 2 precisions, fine grade, coarse grade, 2 precision, but they might have a more gradual. But I don't know the detail how gradual that is. So then this algebraic multigrid, they also have the mix of single and higher precision, only on CPU. On GPU is not much done. And the direct solver have lower precision, LU, higher precision, iterate refinement. And now we move to the mixed precision, the support. We ask people what kind of language support and tools you are interested. And certainly this question, language support, people say uniformly saying something like a template, like a C++ and operator overloading will be probably sufficient or essential support. And the next question is, what tools do you find useful to help you in simplify the analysis of the reduced precision computing? And most people do not know what tools are available. So that's something requires a lot of education, I think, even ourselves. And the wish list for tools is so they can do the following, for example, catching the subtle issues like memory alignment, misalignment issue. And one person said total view. I think a lot of us know about total view, right? Do people know total view we've used? Yeah, so that's pretty much the default debugger for parallel computing for a long, long time. So total view is very effective for memory checking, etc. Even for MPI, say the message communication error. And if it can be, we can build into total view the precision tool, that will be very nice. Julian, you have a question? Oh, no, okay. And a lot of people just say, very often they just use printf. It's still very useful. So the next question is, what tools do you find useful to evaluate the benefits in terms of saving of energy, saving of runtime faster or memory? A couple of people used this, I think Insight is Intel, right? It's, if I remember. Oh, it's NVIDIA for their GPU. Oh, Vitune, yeah, I got confused, thank you. Yeah. So this, several people, they used this Insight. They think this is very useful. But I think from my limited experience with this, it doesn't touch upon the precision. It's mostly about the performance profiling of where the code, how the GPU utilization, high or low, like that. And then people say, manual insert timers and allocation tracking will be doable. For C code, for example, when you do a malloc, you can customize your malloc to do some tracking in terms of how large this memory is allocated. And when you do a free, your customized free will tell you what's the current peak memory is decreased. But this is challenging to do for C++ code, because your C++, when you do object or new something, it's not so visible to you. You cannot manually to do the profiling. So the last, almost the last question. So the 8th and 9th question, this is about a mixed precision adoption obstacles. How disruptive it is. So people say very disruptive. And several code, they are not C++ based. We will have a significant needs to rewrite significantly. And like a PET-C, for example, is a big code, but they build object-oriented concept using C. And for them, even to support a real and complex is already quite a big challenge. So if you use the C code based, you have to double, triple the number of functions you write the code. And difficult to support iterative solvers. I think that's not surprising. And then we asked about whether the third-party library, TPL, third-party library, could help you if they are, have a good support. So generally, they say it's good. So the last question, the wish list. It's a long wish list. We can probably, since I still have, what time? I should stop, like 2?
Yes, I think we have technically up to 2:15.
Oh yeah, I have enough time. So the wish list for vendors, we ask specifically for vendors. There are several bullets here. One is they want to emulate a higher precision competition with a lower precision hardware. So that's something people are already doing. And then provide a high-level libraries that could encapsulate the complexity of emulation. And the second bullet is better mixed precision support for HPC workloads. So for example, provide a mixed precision kernels for sparse matrix operations and decouple FP32 from FP32 storage from FP64. So this is already done in the memory accessor concept, right? And the third bullet is having more uniform interface. So for example, tensor cores have a variety of matrix size and input-output types, which require user to tailor their codes for each architecture. And again, so this is some topic in our software breakout session. We have a lot of discussions with co-design breakout, also with the approximate computing breakout, how to develop a uniform interface. So we will write this in the report. It turns out that maybe even from ground up, from very low level, BLAS level, we may need to have an extra argument or something to allow user to give us the intent, what accuracy they want. Then internally we can do some computation faster with a lower precision. And the next bullet is having wider compiler support for the various types. Then FP16, so as I said, people wish to use FP16, but again, all these libraries, they want to go beyond the GEM or BLAS2 functions in the GPU. And then provide APIs with the flexible input types. So that's another question. Since a lot of our libraries, even BLAS right now, we don't take FP16 type, right? So that last bullet is the one actually I'll spend maybe 10 minutes to talk about it. It's very relevant. A lot of discussions around this topic is they wish the vendor can provide a tool that can help us identify where lower precision is sufficient. For example, you run the double precision code first and reports back to say, and lower the precision to single precision, then say where the results go wrong, and then which variables we have to use double precision. So then that leads to my last part of the talk is about these automatic tools for FP analysis and precision tuning. So before I go this, maybe if people have questions about this survey questions, survey answer, or if you have more. No, not for this crowd. Yeah, so right now the question is whether C++ can support you to print out the type you specify for FP4. I think right now it's not in the standard, right? Yes, yeah. Not decimal value. Something human readable, not assembly binary. Okay, so let's move to the tools. So this actually comes very timely, this workshop and also the hardware, and then some of colleagues came to our group to this topic came up, all happening this couple of months. So it's like everything, everywhere, all at once. So it's good. So in December, I think it's December or January, it's a CES conference, right, John? It's this in Las Vegas, this commercial, it's like the big tech conference in Las Vegas every year, every January. CES, right? Yeah. So CES, NVIDIA announced this Rubin chip. It's coming. It's not in the market yet, but it's coming. So the significance of this is that it's going to be at NERSC will be the next machine. It's called a Doudna. This machine will be in place in later 2026. So that means it's going to be there. And so NERSC people, they are anticipating what's the impact. So you can see that this table, it shows you the performance comparing the different generations of this NVIDIA GPU from Ampere, the A100, let's say, and Hopper, then Blackwell, now the 2026 Rubin. So if you look at this FP16, the matrix operation, it's very good. It's over 10x faster by going from 5 years ago. So 5 years, you get 10x faster. And then if you do FP32, it's only the vector operation. you also get quite a bit. You can get quite a bit speed up, over 5, 6 times speed up. But FP64, that's the topic people have been talking about. It's staggering in terms of speed. Not only that, you actually could go down the performance. So if you are just stick with FP64, you are not really not in good shape. So, but if you look at the speed between here for the upcoming machine, you could get more than 100 times if you are able to change your algorithm to be able to do from FP64 vector to use FP16 matrix. Yeah.
One question, is it FP32 or TF32?
It's the matrix version, so I think maybe it's T, the tensor core you're thinking about. Is that? Oh, not TensorFlow, no.
Real FP32?
Yes, yeah. All right, so that's the hardware-driven, hardware pushed us to think about this. So then recently, because of this, the NERSC staff, NERSC people, and also some application people from other division at LBL, they came to our group to say, to see how we can do mixed precision, lower precision first, then mixed precision second. So started about 2 weeks ago, we are working on a proposal. It's an internal LDRD proposal. John knows what it means. It's an internal proposal to get a small amount of money, seed money, to start something. So essentially what they want is to explore lower precision and then look at the NERSC cycles. So NERSC cycles, they are used by these kind of codes. So one class is accelerator fusion plasma code. It's encompassed in this BLAST T. And they have 2 kind of code. One is WAP-X, one is IMPACT-X. So WAP-X, some people probably recognize this. It's a pretty high profile code. I think it's 2 years ago they won the Golden Bell Prize. So it's led by Axel Huber. And another type of application is from material chemistry. And I think, Jim, we have worked with these teams quite a bit because in the past they are heavy user of scalar pack for many, many years. So this kind of code has VASP, Berkeley GW, Quantum Espresso, etc. So this code, they were not apart from Berkeley GW, but VASP and Quantum Espresso, they were not developed at LBL. Both of them, I think VASP is from Austria, and Quantum Espresso is from Spain, if I remember correctly. So these 2 classes of codes, they use more than 50% of NERSC cycles. So the implication, that's why they came to us, that they want to, from this table, they really want to look at a lower precision. Okay, so then we started, as I said, we started looking at this only 2 or 3 weeks ago, just to prepare for the getting this proposal into the lab. So we started doing some survey of tools, automatic tools. And so if you look at the tools, there's to help you in terms of accuracy analysis. So there are several categories. The first category is guaranteed methods using, say, interval arithmetic or affine arithmetic. And as we know that this interval arithmetic, you can do small amount of calculation. Then beyond that, your interval, it becomes too big. It's not so useful. So basically, 1 is not so useful in practice. The second category is, they can compare between several precisions. But again, if your problems is very ill-conditioned, even just using the existing, say, the supported double single, these precisions, you may not get a very good reference. So the third one is a lot of the tools, they are actually using this stochastic arithmetic. So like using this SASTAC is using random rounding. That's probably pretty easy to do. Then you treat each result, your final result as a random variable. Then you do a lot of samplings. Then you compute the sample mean and the sample variance. There's a typo here. Sample variance to give you some confidence of the computed result. Another kind of arithmetic is Monte Carlo arithmetic. I don't know too much detail about this. In literature, it's very widely used, the MCA. So it's randomly perturb each operation using, say, machine precision. Then probabilistically estimate the final result with, again, with multiple samples. So these multiple samples, it could be problematic. It's expensive because each sample means that you run your big simulation code once, right? And in order to get a good statistical, meaningful result, you need to run not just 2 times, probably 10 times. So another thing is we know about this work, but I'm very happy to be able to talk to Steph and Fabien. You know, they are I think the 2 experts here about the tools in this group. So this Cadena is using discrete stochastic arithmetic. Again, I don't know too much about this, but if you want to know more, you can ask them. So basically, for 2 and 3 options, they have fewer guarantees compared to 1, but they are more practical than 2. So then I will give you our survey about the several tools. It's not comprehensive, but you can see rough idea underneath what they are using. So the first tool I like the most is it's called Varu or something. It's open source. It's based on Valgrind. So actually, and then from it's a binary instrumenting the binary code, so DBI, so that they can support many languages. It's not a source level instrumentation. And it's very easy to use. So for example, their workflow is the front end. You can, they will replace FP instruction with a variant of this, what you do from user point of view, you will just say MPI wrong with some argument and the Valgrind. We all use the Valgrind, right? And all you need to do is to say, specify the tool I want to use this Varu, and then with some options. So the back end, what do? Is they implement several variants of the FP instructions, as I mentioned in the previous page. So it's including SASDAC, including Mac, MCA, sorry, not Mac, MCA, etc. And then the user, this option, you can specify which internal FP instruction I want to use. So when you specify one of them, they will use one of them to replace the original double precision, for example. And then post-processing, again, is based on the statistical mean. You know, they will tell you the accuracy, whether you lose something. And they have some capability to address the mixed precision. So that's one kind, but I think this one is, if we can get it to work, is probably most simple. You just do Valgrind. So the second one I want to mention is Verificalo, it's called. And this one, it's also very good. It's not, user doesn't need to worry about too much because they instrument the LLVM compiler, the intermediate representation. And then to replace each standard FP operation by this Mac arithmetic. So it's transparent to the user, and then they can support most major languages, including parallel stuff. But internally, they probably very often they use MPFR to compute these max samples, which means arbitrary precision could be slow. But we don't have experience yet. The thing they use to overcome this slowness is because it's Monte Carlo sampling, so it's massively parallel, embarrassingly parallel. So you run this in the parallel to do the parallel sampling. So even if each sample is slow, but hopefully you get some, mitigate some of the problem. Another tool is called FP Checker, which is also very, very easy to use, I think. But limitation is it's only detect FP exceptions, but that's, it's still quite good. And the reason it's also very easy to use is this is extension to the CLAN LLVM compiler. So when you use their compiler, you will just say CLAN++ with this dash FP checker to do the compiler. You don't need to change your source code. And they can support various HPC stuff. So the flowchart here is during the compilation phase, your CUDA program, for example, you run through this LLVM compiler. It's generate code for the device code and generate code for the host code, and then binary. So then all these, they modify the internal representation, intermediate representation, to stick in the core to their runtime system to check each operation, whether there's a floating point exception. So during the execution, you will just run through this, very simple. And then in the end, you get a very detailed report. They can tell you the exact location of your file where the exception then occurred, for example. And the last one, not the least important, is actually the one, this promise we talked a lot. So I think after this, you should certainly talk to staff and Fabien. So the idea here is that you try to optimize to find the optimal set of variables in your big code, which could use lower precision. You want to maximize. Suppose you have 100 variables, maybe 60 of them can be single precision. Only 40 needs to be double precision. So that's the goal is here. And then behind the scene, behind the hook, they are using this discrete stochastic algorithm, DSA, and they support HPC code. So the fundamental technology used is pretty widely known in the tools community. It's called delta debugging. So in the beginning, your program is double precision all the way. So then you will say, I change all the variable to single precision. And certainly it's not good. So for example, you see the result is not good. Then you will say, divide the code into two parts. One part change to single precision, the other part maintain to be double precision. And then you get the result. If the result is still not good, so that means that this part, you have to continue to do the binary search to decouple into double precision, single precision. So you just keep doing like that. So it's a recursive bisections kind of thing. So in the end, something, will tell you maybe this is terminate here. So that tells you maybe 40% of the variables, they can be single precision. So that's the idea. But there's a lot of things going on behind the scene. So you can talk to staff and Fabien. So let me conclude. We have a lot of good news about using lower precision, mixed precision, but there are a lot of obstacles for adoption beyond the numerical linear algebra. And the tools could be a very good bridge for this. And Fabien actually pointed me to this survey website. You can certainly go there to take a look. But it's overwhelming. I took a look, pages of tools. So the question is, how shall we provide advice? And what are the important things? Certainly, people want ease of use, whether it's on GPU, and the speed. If you instrument the code, whether it's a binary dynamic instrumentation or static instrumentation, what's the speed of instrumented code? And another important issue is how these tools can be composable. Because, so for example, I mentioned the FP checker. It only checks the exceptions, so that's not sufficient. If we want to use both the FP checker and promise, how does this interact with each other? So there are still, I'm sure there are more questions, so we just started looking at this. So hopefully, I'm hoping our proposal will get funded, then we'll start working on these tools for these applications. Maybe in a year time, I can report back. Okay, I'll stop here. Jim. Yes, so it's very similar. So they both use delta debugging. So in fact, I asked Cindy in the very beginning several weeks ago when I started looking at this problem. It's I think the only issue is it's not so actively maintained. So she said it's mostly her and her student are using that. So if we need to use, we will have to work closely with them. Oh, the top level algorithm is the same. It's delta debugging, and maybe you can say a little more. Do you know more difference, Fabia? Okay. Yeah. Yes, yeah. I didn't put on, I ran out of time. I read the paper. I was actually talking to Rio. So that's a Raptor. It's also LL instrument, the LLVM, the intermediate IR. Yeah. So from user point of view, it's still very transparent. Yeah. So we'll write all this. If you have any input to us, we'll write this in the report in our report. David. No, so you give one configuration input, right? Then you run multiple times. Because internally they have a stochastic rounding for stochastic arithmetic. Yeah. No, but test suite is application. You develop test suite. The tools, they won't have a test suite. Yeah. Mm-hmm. Mm-hmm. That's very philosophical. So actually, one of the topics coming up again and again related to energy, there's no good way to measure the energy. I don't know whether Jack Pappy could give you something. Okay. Since we with Jim, we are working on GP-tune, we often say minimize the memory or time or combination of memory time, but then we don't have a good way of say this user code give us the memory usage, the energy. Oh, right, from NERSC. Okay, very good. Yeah, very good. Yeah. More, David? I see. Okay. Yeah, that's a good question. Is adapt in one of the two survey? I think I read some. Oh, no, okay. Oh, okay. Okay, that's good to know. Yeah, thank you. Okay, okay, that's very good. Yeah. Mhm. All right. So I think.